direct applications to structural molecular biology. There's some topology in there. So let's go and see. It's about the intrinsic volumes of space-filling diagrams and their derivatives. Space-filling diagrams are a particular model of a molecule. In particular, I'm interested in proteins. Intrinsic volumes in 3 dimensions are the volume itself, the area, the mean curvature, and the Gaussian curvature. And I also want to say that this is a long-term collaborative work with Patrice Koehl from Davis, Robert Bryant from Duke University, Michael Levitt from Stanford, and Arseniy Akopyan, who was at ISD and just recently moved to Florida. In fact, there are 4 papers that were published on a topic. The first one on area, the second one on volume, third one on mean curvature, and the fourth one on Gaussian curvature. And they're separate papers because the derivatives are in fact all quite demanding and lots of formulas. And although they have a similar basis, a common basis, in fact, so I can talk about all of them in one talk, they are individually quite different. And also I want to mention that I consider the weighted version in each case. And weighted is just some real number, some real weight measure, modeling some kind of physical property, such as hydrophobicity, for example. All right, let me first motivate the work a little bit. It comes from molecular dynamics. So molecular dynamics is this idea that we could model molecules if we know their structure, their chemical structure, by implementing Newton's law of motion and then simulate it on a computer and then find out how the molecules move. In particular, interesting is this is for proteins because proteins come out as a string, more or less, and they fold up into a particular shape. So when proteins are active, they have a particular shape. Each protein has their own shape. And trying to find out what this shape is the protein folding problem, which is still a hard problem nowadays. When you do molecular dynamics, there's all kinds of ingredients. In particular, so first thing I told you is we need the chemical formula so that we can create a geometric object which is connected in the way the formula dictates. Then we need energy functions, in particular electrostatic, polarization, van der Waals forces, and the second is WNP for non-polar interactions. Is a complicated formula, and some people believe that the reason why protein folding is still an open question nowadays is because we are not very good in modeling the energy, the forces. And so this talk is a contribution to modeling forces that could be used in molecular dynamics, in particular in protein folding. Oh, by the way, I should mention, even though I try to make my talk within 40 minutes, if you have a question in the middle of the talk, don't hesitate to ask. Because also it's a favor to me, because talking to my computer for 40 minutes is not a very joyful enterprise. So if you can loosen it up by asking a question and I try to give short answers, that'll be cool. All right, now let's get to space filling diagrams. So there's all kinds of different ways of modeling a protein. The middle one is maybe the most common one, the stick diagram, where the covalent bonds are represented by edges connecting atoms. On the right, you see a space filling diagram where the atoms are blown up a little to make spherical balls that overlap. And the reason for doing this is because the protein interacts with a solution, which usually is water. Water consists of water molecules, which are pretty much spherical. So the spheres of the protein model, like in robotics, the interaction of the water spheres. It's also called the CPK model. Pauling was one of the people initiating this. And very common in publications is the cartoon model, which is kind of a sketch of the way the protein is connected as a backbone with trees hanging off. That gives you a little bit of an internal structure that is maybe hidden in the space filling diagram, which shows you more how the protein interacts with its environment. The solvent accessible model, which is a particular space filling diagram, is due to Lee and Richards. So that's from 71. And in some ways, this is the model that makes structural molecular biology geometric. That's why geometry is interesting. And I want to mention also a paper by Eisenberg and Lachlan, where they propose that in the model for the nonpolar interaction energy is something related to the area. So I have an index I running here. This is for all the atoms. So the ith atom contributes an area sub I to the surface, and there's a weight depending on maybe hydrophobicity factor. But right from the beginning, there were some voices which said, well, maybe it's not just area, maybe it's also volume. So there were some indications that for particular small molecules, the volume is more important than the area. This motivated the morphometric approach. At least that's my interpretation. This is due to Koenig, Roth, and Mecke from around 2000. And they say that instead of focusing on area or volume, might make sense to look at all intrinsic volumes. So includes the mean curvature and Gaussian curvature. I remember years ago, I talked to Roland Roth about this, and then my first objection was that the mean and the Gaussian curvature could only be very small contributions to the overall sum, to which he agreed, but he also said that if there are small pieces missing from the energy function, the whole thing goes wrong very fast in molecular dynamics. And that's in general the observation that in molecular dynamics, it's very unstable. Small errors blow up, and then after a while you see something which has nothing to do with reality. Okay, anyway, so the morphometric approach is this sum here. We have the volume, the area, the mean curvature, the Gaussian curvature, contributions of all the atoms, each weighted with a WI. And we also weight the contributions of the 4 intrinsic volumes by mu sub i's. And the underlying motivation for this proposal was a theorem by Hadwiger, Hugo Hadwiger, from 1951, which is known as the Characterization Theorem. And if you didn't see this before, let's go through it. It says that measures for convex bodies in d dimensions that are continuous, Hausdorff continuous, invariant under rigid motions, and also additive. Additive means that the union of two bodies, the measure is the same as the sum of the measures minus the measure of the intersection. So all these measures that have these properties 1, 2, 3 are linear combinations of the intrinsic volumes. So this somehow puts the intrinsic volumes at center stage when the topic is about measures of bodies. In particular, this was for convex bodies. I'll introduce the intrinsic volumes more detailed pretty much now. Yeah, so let's jump into the discussion of intrinsic volumes. The way I like to do this is usually with a Steiner polynomial. So here, imagine a convex body. In this drawing, imagine the blue cube. So this is a blue cube. You only see 3 edges, but there's a cube underneath. It's convex. It lives in 3 dimensions. And I'm going to thicken it by a radius little r. So this is called the parallel body, K super r. It's really the Minkowski sum of my convex body with a ball of radius r. And you can imagine the cube thickens, and then also it gets rounded edges and rounded vertices. And Steiner polynomial says that the volume of this thickened body is a degree 3 polynomial, exactly. There's no approximation here. And this degree 3 polynomial has, of course, 4 coefficients. I call them A0 to A3. And these 4 coefficients are the intrinsic volumes. So if you look at this, A0, of course, is the volume of the cube. Because for r equal to 0, the thickened body is the same as the cube, so it must be the volume. A1 is a surface area, which is intuitive because at first we thicken only a long area, and so we get a thickened plate on top of every face. But then there's also around the edges, there's this cylindrical, circular cross-section pieces that interpolate here. And A2 here is the mean curvature. Now, mean curvature, you could have a question because mean curvature is traditionally defined for smooth bodies. Here we don't have a smooth body, we have a polytope. I'm going to talk about what mean curvature in a polytope environment should mean. And then there's also pieces at the vertices. So for the cube, you have 1/8 of a sphere of a ball sitting around each vertex. Together, they form a whole ball. And so A3 is the Gaussian curvature. And this makes up the Steiner polynomial. If this makes sense so far, let me go a little bit deeper into the mean curvature in this case. So I'm talking about what could A sub 2 mean, mean curvature. As I mentioned earlier, what I'm talking about here is the volume contribution along the edges, these cylindrical tubes. And the volume here is, suppose that an edge length is 1. Then I have a quarter cylinder along each edge. The volume is pi over 2 times the edge length. No, sorry, pi over 4, because the disk area is r squared pi over 4 times the length. And the curvature contribution along the cylindrical piece is along the circular part, which is the angle, how much it turns. That's pi over 2. The length is 1. We have 12 edges, so that's 6 pi. And then I divide by 2 because I take the mean curvature, which means the average of the curvature around the circular curvature and the straight curvature, which is 0. Okay, so in a polytope situation, the mean curvature would mean a sum over all edges. For each edge, I take the angle between the 2 normals of the faces, left and right. I multiply with the length. I sum it up and I divide by 2. Oops. I also want to introduce a connection to stochastic geometry, namely Crofton formulas. I don't know whether you came across this topic, but it's closely related to what I'm talking about. And what it helps us understand also is how to go from convex to non-convex bodies. That there's really no limitation because Hadwiger's theorem started with convex bodies. So Crofton's formula says that the intrinsic volumes have this integral description. So AP is the pth integral intrinsic volume. It's an integral of the body K intersected with a p-dimensional plane. So for example, for the volume, we have A0. we integrate over points. And an integration is of the Euler characteristic of the plane with the body, the intersection. And then we integrate this. And then there's a constant C sub p. Okay, the interesting case is really the area. In the area case, we integrate over all lines in space. So here P would be one-dimensional planes, so lines. And then we intersect the lines with the body. We integrate, so if you have a convex body, the intersection is always just empty or an interval. So the Euler characteristic can only be 0 and 1. So you really just integrate over the lines that intersect the convex body. In a non-convex case, it's a little bit more complicated because the line intersects in pieces, and then the Euler characteristic of the intersection is the number of pieces. And you integrate this over all lines, you multiply with this constant Cp, then you get the intrinsic volumes. And this constant is for all bodies. It depends on the dimension, but it depends on the dimension of the intrinsic volume. So in 3 dimensions is from 1 to 3, from 0 to 3. But they differ in different Euclidean dimensions. But they do not depend on the body. So we could figure out the constant by looking at the unit ball, what the result of the unit ball is. And I do this in just one case. Maybe the mean curvature. So the mean curvature for the unit ball is the surface of the sphere, which is 4 pi. The mean curvature at that point is the average of the 2 principal curvatures, which in this case is 1 plus 1 divided by 2. So it's 1 integrated over the area is 4 pi. Okay, so we would like to have 4 pi as the answer. Now we integrate over all planes intersected with the ball. Now, how many planes do we have? For a plane in 3 dimensions, we first fix, say, a normal direction. The amount is 4 pi. And then we take an offset from the origin, which is from 0 to 1. So the measure of planes that intersect the ball is 4 pi. And then for each one, we get Euler characteristic 1, because the intersection is connected and contractible. So this gives 4 pi, so the constant is 1. Maybe not surprising. This was for the mean curvature. For the area, maybe for the area, it's more interesting because there we talk about lines. When you talk about lines intersecting the unit ball, then you again have to choose a direction. Since opposite directions are the same, I just take 2 pi for directions. And then I take a point in the normal disk, which with area pi, so I have 2 pi times pi, so that's 2 pi squared. That's my integral. And if I multiply with 2 over pi, I get 4 pi, which is the area. Okay, so these are the constants that show up in the Crofton formula. And now I would like to get more specific about the 4 intrinsic volumes for space-filling diagrams. First, the main topic is derivatives. But before I go to derivatives, I show you the formulas, how they look. What are the ingredients? So there's a lot of symbols here. And a few we already saw before. The WIs are just weights. They don't vary. Nu sub I is, so I mostly work with fractions. Nu sub I is the fraction of the ith ball contributing to the volume of the space filling diagram. Sigma is surface area. That's classical notation from stochastic geometry. So it's the fraction of the ith sphere that shows up on the surface of the space filling diagram. Ri is the radius. And in the derivative, I assume the radii do not change. All that changes is the locations of the atoms. They move around. And as they move around, the fractions, the nu sub I, the sigma sub I change. Then we also have double indices like sigma I, J is I have the ith and a jth sphere. They intersect in a circle. This circle contributes to the surface of the space filling diagram a fraction, which is sigma ij. Phi ij is an angle that we'll see later. Oops. Lambda ij is a certain length, we'll see later. And then we'll also talk about the alpha sub I. Those are particular fractions that show up in a Gaussian curvature. Okay, so roughly you don't have to remember exactly what those are, but the way the derivatives get computed is take those formulas, the new I, sigma I, ij, and so on, they change with the location. So we have to compute the derivatives, and we do this, and then we get the result. The only trouble here is that things get complicated, and to keep complication to a minimum is kind of the name of the game. In all four intrinsic volumes, the basis of why we were able to do it without an unsurmountable accumulation of complications was because we can use alpha shapes to compute fractions of spheres, of balls, of disks, of circles. And so I'll talk about this a little bit. And this goes back to Kratky. He's a physicist from Vienna, and then he wrote some math papers in the 70s where he says that if you have a set of spheres, or in general shapes, but he was interested in spheres, then you can compute the volume by inclusion-exclusion. So I just wrote down the inclusion-exclusion formula. The trouble with this is it's over all subset of S. So there are exponentially many subsets. And so this is a nice formula. It's exact, but it's extremely large. But he says that if you have spheres in 3 dimensions, then none of the subsets has to be larger than 4. So the dimension of the sets are at most 3. And so this would limit the formula to length 4th power of the number of spheres. He didn't exactly show what the formulas are, but he gave a method of reducing longer formulas until you arrive at a short enough formula. There is, however, a way of doing this directly with a Voronoi decomposition. So here I draw a union of balls in 2 dimensions. It's a little easier. This is called the Voronoi decomposition. Namely, for any 2 points, I draw the bisector. And you see that the bisector is not exactly in the middle between 2 points. And that's because the disks don't have the same radius. So I use what's called the power distance. I get straight lines. It looks like the Euclidean diagram, except that the bisectors are not in the middle. And now this decomposes the balls into pieces. And those are the fractions I talked about, the nu sub I, the volume fraction of some ith sphere. Sigma I is the surface area fraction, because usually not the entire sphere is on the boundary, but only a fraction. And the double indices are about line segments between 2 disks. So in 3 dimensions, it would be 2 balls separated by a disk and a fraction of that disk that shows up in the Voronoi decomposition of the molecule. And the inclusion-exclusion formula I told you about can be derived from this Voronoi decomposition. Namely, there's a theorem that I proved in '95 that if you go over the alpha shape is the dual complex of this Voronoi decomposition. In the picture, you see a drawing. It consists of, in a plane, it consists of edges between 2. Also triangles if the 3 regions or 3 pieces of balls meet at a point. In 3 dimensions, we also have tetrahedra, when 4 balls, they form pieces and then they meet at a point. So this is a simplicial complex. It's called the alpha shape, or short alpha. And what I'm saying is that if you take a sum over all the simplices in the alpha shape, alternate by dimension, and take the volume of the intersection of the balls that correspond to the simplex, you get the correct volume. So this is, again, a formula where the largest set consists of 4 balls, just because they're tetrahedra and there's nothing else in 3 dimensions. On the other hand, the length of this formula is much less than 4th power of n, because the alpha shape is small, in particular for uniformly distributed points, which molecules usually are. This is only linear size. So this is a linear size formula in expectation. And it's very convenient. So I have this inclusion-exclusion formula to get the volume fractions, the area fractions, and so on. I don't go into the details, but I think it's plausible that all these things can be computed very easily from this simplicial complex. In particular, I always talk about fractions of balls, fractions of spheres. So I want to say one more thing about this. The inclusion-exclusion formula I told you about is about intersections of balls, pairwise, triple-wise, 4-tuple-wise intersections. In the alpha shape, those intersections are very nice in the sense that triple-wise intersections, for example, you can always cut it into 3 pieces by going through the spindle, drawing a line through the spindle here. This is called an independent configuration of balls. And so when you implement this, there's only one case, as opposed to generally, when you have balls intersecting, they can have many different configurations. And by computing this, and then you get the fractions just from computing angles, areas, and stuff. All right. So now I get into the formulas, and we have 4 formulas. I'm not going to talk about all of them, but I thought I'll talk a little bit about the area formula and about the Gaussian curvature formula, just to highlight certain features, because each formula is a little too complicated anyway. So here is the area derivative. Let me remind you of the setting. So I have a molecule with n atoms. I'm interested in the coordinates of the centers of these atoms. So I have 3 coordinates per point. So 3n coordinates altogether. So my description of the molecule is a point in 3n dimensional space. The radius is fixed, so that's not part of this function. A is the area function. And I want to compute the derivative of the area. So that's in 3n dimensions. And I write x for the position, which means there's a point in 3n dimensions. And d is a vector in 3n dimensions, the motion vector. So it allows every atom to go in its own direction. Call it the momentum. And if I find the gradient, so little a is the gradient of this function, then the derivative is just a scalar product of the gradient with the momentum in this direction. Okay, so it boils down to finding the gradient of the area function. And this is the formula. Namely, this a 3n dimensional vector, is a concatenation of a sub i's. Each a sub I is obtained for the ith sphere or ith atom. That's this formula. Let's see what shows up here. There's a uij, that's the unit vector from the center of the ith to the center of the jth sphere. I think I have it the other way around. I go from the jth sphere to the ith sphere, unit vector. And uij is, I have another slide for that. And then I have coefficients aij, aji, and so on. And those are all ingredients, like these are all numbers, just weight, length fraction, radius, distance, Euclidean distance between centers, differences between squared radii. So not worth mentioning. What's worth mentioning maybe is there's this uijk. There's a term that depends on 3 spheres. And actually for a long time, I thought that the area derivative could only depend on pairwise interactions, like two spheres, they move. So if they move about, then the area gets larger. If they get closer, the area gets smaller. And then it's also possible that one sphere rotates about the other one, keeping the distance between the centers constant, in which case the area would not change. But with the interaction of further spheres, it can change. Here's a picture. So I have a sphere in the middle at the center. This is the big one. And then the sphere is intersected by a sphere in a cap. This is this colored one, shaded one. And then there are some dotted ones that interact on the boundary. So if this shaded sphere rotates around the big sphere, it moves sideways, then it gains area here at the end, and it loses area in front. But where it overlaps with additional spheres, nothing changes. At least not as far as the first two spheres are related. So I found this interesting because this means that rotational motion have a direct influence on the derivative of the area, or on the area and on the derivative. So it could very well be that this rotational motion has a special role in protein folding. I don't know whether that's true or not, but I think it's possible. I wanted to explain this UIJK. So IJK are three spheres, and UIJK is a vector from the center of the kth sphere, xk, normal to the line of xi, xj. And this motion quantifies what I explained roughly when what happens when there's a rotational motion of one sphere around another one. Okay, so much about the area derivative. I wanted to say a few words also about the Gaussian curvature derivative. To the outset, I would like to mention, just in order to avoid confusion, the Gaussian curvature, of course, obeys the Gauss-Bonnet theorem. So if a surface changes without changing its topology, then the Gaussian curvature does not change. And the surface area of the space filling diagram, to a large extent, does not change topology, does not create tunnels. So as long as there's no such change, the Gaussian curvature should be constant. So what am I talking about when I talk about curvature? The whole game changes when we have weights, because each sphere is weighted by its hydrophobicity. And so small changes change the contributions of spheres or balls to the Gaussian curvature, and those pieces get weighted. And so even small motions that do not change the topology do change the weighted Gaussian curvature. So that's why this Gaussian curvature is actually interesting for derivatives. Okay, so here is the formula. Let's see, let's take it apart a little bit. The first part is just the Gaussian curvature contribution of a sphere. So we have the spherical surfaces. The Gaussian curvature at a point is the product of the principal curvatures. So it depends on the radius, but then we just add it up for all the spheres. There's some interaction along the circles where the spheres intersect, because the circles have also a curvature. And I should imagine, since this is now again not smooth, so I have to have a discrete model for it. I imagine that instead of a circle where the two spheres intersect, I have a little torus patch interpolating between the two spheres. And so this torus patch is a kind of a narrow strip, and then there I have Gaussian curvature. And And this gives the Gaussian curvature along this torus strip in the limit, when the torus strip gets arbitrarily close to the circle. And there's a lambda sub I, and this lambda sub I somehow is the projection of the two normal vectors to the spheres where they intersect. I don't really have an intuitive explanation of why this length shows up, but it does. But I wanted to talk about the next term anyway. That's I thought more interesting, namely the Gaussian curvature is really concentrated a lot at the intersections of three spheres. So these are three corners where the three spheres come together. And there is a whole bunch of Gaussian curvature contribution at such a corner. And I need to divide it up into the three spheres because they have different weights. So I have to come up with weights with coefficients alpha 1, alpha I, alpha j, alpha k that give the portions of responsibility to the three spheres for this corner. And then this is multiplied with a solid angle. This is a solid angle between, for each sphere at this intersection point at the corner, I have a normal vector. So I have three normal vectors. And this is the solid angle spanned by these three vectors in 3 dimensions. But I wanted to talk about this alpha sub I, these multipliers. Because there's something maybe slightly unusual happening. So I've drawn this picture here. What you should imagine is there are three spheres meeting at the corner. I draw this little ball at the center, with its center at this corner. And there are three vectors, n sub I, n sub j, n sub k, which go to the centers of the three spheres. So this triangle here, spherical triangle, represents this is the solid angle that I was talking about. And I have to divide this solid angle into pieces. Something I didn't tell you earlier, so a similar question comes up already in a mean curvature. In a mean curvature, for example, there's a contribution along the circular arc, and there are two spheres coming together. And then I have to ask myself, how much of the curvature do I have to want to the sphere left and right? And there we have a geometric argument that says 1/2 each is fair, because in the limit, when you shrink the torus, that's how it gets divided up. But here, there's no 1/3, 1/3, 1/3 share, because the spherical triangle has different angles, two-dimensional angles. But we can divide it up. So we already decided an arc, we divide into two. This is what I said earlier for the circle arcs. I can connect the centers of the arcs to the circumcenter of the triangle. This is the point where I draw a circle through the corner, through the vertices of the triangle. And this divides my triangle into 3 quadrangles. I have 3 areas, and those are my alpha I, alpha j, alpha k. But we have to understand that it's possible that this point Z is outside of the triangle. In particular, if at some vertex, the angle is larger than 90 degrees, then the circumcenter is outside. And then my division into 4 quadrangles is still a division into 4 quadrangles, but I have a -1 and 2 positive ones. So a contribution could also be negative to the Gaussian curvature. At least the geometric view is, the geometrically satisfying view is that. All right, so I'm close to my 40 minutes limit, and you didn't ask questions yet, so I assume you will ask some after my talk. I showed you the intrinsic volumes, the intrinsic volume derivatives, at least some snippets, the more interesting ones. One thing I wanted to mention also is the derivatives are discontinuous sometimes. And with this analysis that I showed you, it's possible to figure out exactly where the discontinuities are. There's a few types now I don't remember, maybe there's 4 or 5 types or something. The simplest type is when two spheres meet exactly. Then when they get together, the area that they swallow up at the very beginning is discontinuous. So here the area derivative gets discontinuous. So the way I think of this is that the spheres define lower dimensional manifolds in R to the 3n. That's where the derivative is discontinuous. And why I think this is important is that when you implement this, of course, numerically, and there are instabilities. And with this method, it's at least possible to figure out if there's instability, whether this is because of a discontinuity, this just comes with the problem, or whether it's some numerical instability that comes from a particular method that is used. And this is, I think, a luxury that I have not seen in other methods for computing derivatives, which are numerical and not discrete. Here, everything is discrete, so everything is decidable, except in the end, of course, we have lots of real numbers that get added up and multiplied. And I think this is all I wanted to say. Thank you very much.
Thank you very much for your presentation. I guess we have virtual applause. And if people want to ask questions, perhaps it is best if you put a Q into the chat, because then I know the order in which questions have been asked. I don't see any Q yet, so maybe then I myself start with the first question. In protein folding, which was your original motivation, the question is to find the minimum of the energy functional, and the energy functional for protein folding has many different local minima, and that is what makes the problem difficult. So here, what would the minima look like? How many minima would there be, and how could you possibly find them?
I have no idea. And I don't quite buy into the idea that the important thing is the global minimum. I think it's also the funnel that leads into a minimum. If there's a non-global minimum, which is very easy to reach in terms of motion, I'm sure that's the naturally one that's used by nature. But I cannot say anything more about the minima and the landscape of energy than what's out there in the literature, because I'm just saying how I can compute it and how I can get the derivative. But I don't change the energy function. I don't study the energy function otherwise.
Yeah, of course. I mean, it may well be that the size of the basin of attraction of a minimum also plays some role. But with your scheme, you could at least derive equations for minima, namely where the derivatives vanish. What would these equations then look like?
Well, you mean all the derivatives? The derivative is zero.
Yes.
Yeah. Yeah, I don't know how far you get with this. Yeah.
Yeah, but I mean, according to your scheme, there should be some beautiful geometric interpretation.
Well, the beautiful geometric interpretation, if you simplify the energy function grossly and make it geometric, if you allow weights like hydrophobicity and all these ingredients that come with it, I think the geometric beauty is lost before you start. At the beginning of the project, I did plan to try to use this in order to answer some geometric questions where the energy functions could be some simple geometric idea. Didn't get this far, so I cannot answer that. But there could be some interesting geometric questions, such as, I think the Kneser conjecture is still open in some dimensions, whether spheres, when you move them together, cover less volume. And this could possibly be used to approach this. but at this moment, I cannot say anything about it.
Okay, thanks. And instead of continuing my own questions, I hand it over to Wei Guowei because he also has a question. Please go away.
Yeah, it's great talk. I just wonder if you can use your method for electrostatics modeling over there.
Can you repeat the question? I didn't understand.
Yeah, my question is, can you use your methods for the electrostatics of a protein? Yeah.
No, the electrostatic is an input to my, so I can use the electrostatics and then compute the derivative. But you have to tell me what you use for electrostatics. I understand electrostatic is a hugely controversial energy function, in fact, and that might be responsible for a lot of the mistakes. But I cannot contribute to improving modeling electrostatics, if that's the question.
Okay, there is another question by Kelin. Please, Kelin.
Yeah, thank you. So I have a question. So you mentioned about these free energies related to the volume area. Is this related volume area and the total Minkowski? Or is it related to the Minkowski function now?
Same thing.
Same thing. Okay.
The intrinsic volumes is one name for this Minkowski function.
And another thing is that people have tried to do the persistent version of the Minkowski sphere. Is it possible that you can apply some of your model along this line?
That I can apply what? Can you repeat?
I mean, the people can do the persistent version. For example, you can increase your volume and you have this persistent filtration process, and then can you observe these properties during this filtration process, and then see it may be related to some special functions.
It's an interesting idea. I would love to see what happens in this persistent version, but I didn't try it, so I don't know. But of course, you can use it. You can see how the derivative simplifies and whether it gets you to the important minima faster, possibly, but I don't know.
I see some people use this Minkowski function now, the discrete version on the images, and they also have these persistencies, and then use it to analyze the picture and the images. And here, this discretization is a little bit different. So maybe the filtration process, you can observe some special properties from there.
Yeah, this makes a lot of sense. Yeah.
Yeah. Okay. Yeah. Thank you.
Yeah. Okay. The next question is by Wojciech Czarkolski.
So Herbert, so you get this model with these balls around, and then you know how to, you try to calculate the volumes of these things. Now, what it's unclear to me is whether, and then you try to find the derivative of these, when they think change. It's unclear to me that, I mean, will the protein fold in order for these volumes to minimize for these areas? Like, is there reason to believe that?
No, but that's not what I wanted to say. But the volume, area, etc., are ingredients. So the driving force is a combination of different things, and one contribution is, the protein has to live within a solution, so its volume moves water molecules out of the way. This requires some energy, and that's the volume part. That's reasonably intuitive. For the surface area, on the surface, it interacts with water molecules. It likes to do it, and hydrophobic, and it doesn't like to do it. So there is this, and then the morphological approach or morphometric approach postulates that it's not only the area, but also the derivatives of that. So the mean curvature and the Gaussian curvature, which makes sense because as things curve, the area of contact is not just the area, but rather also, in particular when it's multi-scale, the curvatures.
Right, yes.
So whether this morphometric approach is reality, meaning whether if somebody implements this approach here and then uses it, gets better results, I very much hope so, but I don't know.
Okay. Thank you. Great talk.
Thank you.